So on Monday in class, we look at some elementary acid-base dissociation reactions in which either our acid was weak or our base was weak. I'd like to go back to that general equilibria and show how we can derive the Henderson-Hasselbalch equation, which is useful once we begin taking a close look at the neutralization of a weak acid with a strong base or a weak base with a strong acid. So let's consider our hypothetical acid HA. And HA is going to be dissolved into an aqueous solution. So HA is aqueous. We have liquid water. And of course this reaction is at equilibrium, so it is governed by the equilibrium constant Ka. And our products will be hydronium ion, which will also be aqueous, and by the conjugate base of our parent acid, A-, which again is aqueous. Can use some algebra to write an equilibrium expression for Ka in terms of reactants and products. So Ka is equal to the concentration of hydronium times the concentration of A- divided by the concentration of HA. Once again, let me remind you that pure solids and pure liquids do not enter into the equilibrium expression. What we want to do now is to mathematically manipulate this expression. So I'm going to take the negative log of the entire equation. And I will obtain the negative log of Ka equals the negative log of H3O plus. Now, from the properties of logs, I can legitimately separate out the hydronium from the rest of the expression, minus the log of the concentration of A- over HA. The negative log of Ka is better known as the pKa. The negative log of hydronium is better known as pH. And of course, I will keep the last part of this expression the same, minus the log of the ratio of A- to HA. This expression is better known as the Henderson-Hasselbalch equation. Real important result that we will use throughout the next couple of weeks in class to solve practical problems. So let's go back to a question that we answered in class on Monday. Let's imagine that we have a 0.1 molar acetic acid solution, and let's imagine that we have 25 milliliters of this particular solution. So if you go back and use a little bit of imagination in our titration setup, our acetic acid would be in this beaker, 25 milliliters of 0.1 molar acetic acid. Of course, this is better known as our analyte. Of course, we have in our probeware setup a syringe filled with a base like NaOH. And so let's say that we have an unknown concentration of NaOH. In fact, the purpose of our titration, or at least one of the purposes, is to find the concentration of this unknown NaOH solution by neutralizing my acidic solution one drop at a time. This is better known as a titration. And of course, in a titration curve, we're going to collect data where we have pH as a function of volume of titrant added, which in this case is the volume of OH minus added. And if you recall from the lab that we did last week, we should obtain a titration curve. It looks something like this. At this inflection point, this is where total and complete neutralization occurs. This is where the moles of acid is equal to moles of base. Moles of HA equals moles of OH minus. Again, to set the stage, because what we're going to do now is calculate some critical points in this titration curve. Then we're going to go into the lab and do an experiment in which we either validate or correct our theoretical predictions. In an idealized situation, the pH that we predict for each point should be equal to the pH that we obtain experimentally for each point. This is part of a pretty massive problem that I will give you guys on a take-home test. It's a classic Gen Chem 2 chemistry examination question. And so we'll piece this together step by step. So why don't we first start by calculating the the pH of our acetic acid solution before I add any NaOH at all, which should be review. So we'll use the ICE methodology to do this. I have acetic acid, which I'm going to abbreviate as HAC, in water. Of course, this reaction is at equilibrium and is governed by an equilibrium constant at room temperature that corresponds to 1.8 times 10 to the minus 5. My products are hydronium. Of course, that is aqueous. And acetate, which again is aqueous. Initially, 0.1 molar. No products are formed. We know that I will convert some unknown amount of my acetic acid to product. So at equilibrium, I'm 0.1 minus X, which we approximate as equal to 0.1. Again, because our initial concentration is much larger than our Ka, and I'll have X for each of my products. Now applying the equilibrium constant in terms of reactants and products, we get 1.8 times 10 to the minus 5 equals X squared over 0.1. That's 1.8 times 10 to the minus 6 equals X squared. 1.35 times 10 to the minus third equals X, which equals hydronium. Take the negative log of hydronium, and I find my pH is 2.87. Just like we did in class on Monday. So our initial pH before any base is added should be 2.87. This is 0.1, where I've added 0 milliliters of NaOH. Now let's go back and realize that we had 25 milliliters of acetic acid at 0.1 molar. Now we're going to begin to add OH minus. So now our equilibrium is going to change. I will produce water and I will produce acetate. So I had 25 mils of a 0.1 molar solution. That means I had 2.5 millimoles. And let's imagine that I add 5 milliliters of a 0.1 molar solution. So I've added 0.5 millimoles of base. That means at equilibrium, 0.5 millimoles of this base is going to neutralize 0.5 millimoles of acid. That'll leave me with 2 millimoles. It'll leave me with no base, but it will produce 0.5 millimoles of acetate. Going back to the Henderson-Hasselbalch equation, I know that my pH is equal to my pKa plus the log of A minus over HA. pKa of acetic acid is 4.74 plus the log of 0.5 over 2. And all I have to do now is to mathematically simplify this and I will get a pH. And I hope it makes sense that the pH should be greater than 2.87 because I've begun to neutralize an acidic solution whose pH before I added any base was 2.87. So quickly, I'm going to do this math. So when I plug this in my calculator, I find I get 4.74 minus 0.6, which gives me a pH of 4.14. This is greater than 2.87. My pH makes perfect sense. So I'm going to stop the podcast here. What I would like for you guys to do is applying the same methodology. This method will work until you get exactly to the equivalence point. So in setting this up, let's choose 10 milliliters of base. Let's choose 15 milliliters of base. Let's choose 20 milliliters of base. Let's choose 24 milliliters of base. Let's choose 24.5 milliliters of base. Let's choose 24.9 milliliters of base. Let's choose 24.99 milliliters of base. That's a lot of individual calculations, but I want you to begin to see that the huge jump in our pH is going to occur as I approach the equivalence point, which is 25 milliliters. And certainly I will represent this problem in class tomorrow, and we can also work each of these data points so that you get at least a little bit of experience on how you handle a problem like this.